All right, welcome to this presentation on predictive analytics in healthcare, part 2, where we're looking at predictive modeling in using Python to do so, okay? But more about the predictive modeling, why we do it, how we do it. We're going to start with talking about the preconditions of value. We don't want to do prediction just to do prediction. After that, then we'll move on to the more technical pieces of how do we set up the data, and select and use a model. So on the preconditions front, this is just my opportunity to warn and tell you this is a topic people really like. They want to say that they're doing predictive analytics, but it's really important to evaluate these three things in any use case that is brought to you as a data analyst in healthcare analytics. First of all, will we have the early access to the data that we need? It is surprising how often it is overlooked that people might say something like, we would probably be able to predict that if we knew the DRG. But the DRG is something that happens after a hospital encounter, after a billing process, and so we don't have it during the encounter. And so whenever the data is not accessible, the right data isn't accessible early enough to make the prediction, we really can't use it in that instance. So it's a simple question. Will we have the data in time to make a prediction that is meaningful? It's a question that can stop some efforts that would otherwise really not be fruitful. Number two, a place that I commonly see, this is probably the most common place that I see initiatives fall down in their effectiveness is this actionable? Does it deliver an output that we actually have something to do about? Often people bring up predictive ideas that would be interesting to know, but not that are needed to know in order to change something. Now, it doesn't mean you shouldn't do it just because there isn't a direct action to take. Sometimes the information itself is valuable or it gets you moving the right direction so you can find an action to take, but I would say those are rare occasions that really you should be searching for predictive work that has an action tied to it. Very likely, the people who are bringing this thing to you have not thought through the problem deep enough if they don't have an action to take if they knew this ahead of time. Now, these things can happen in parallel, where you can impress upon them the need to pick out an action we will take with the information as you're engaging in building a predictive model for them. But I just want to put this out there. Don't be surprised when effectiveness doesn't really follow through because we didn't pick out something actionable to do with the prediction. Finally, we do have to figure out if we will be accurate enough to make a difference. And so here we're looking for some sort of benchmark or some sort of practical threshold with which we can measure, is this effective? Is this valuable? Is this worth it? So this can be a creative exercise. This can be looking for something like, do we do better than a naive prediction? And if there's value in that, then we're in good shape. If there's some sort of cost involved, this is a great time to incorporate that, to figure out what is the cost of being wrong and how often are we wrong, based on the measurement of the accuracy of the prediction. So this is best solved by getting this into common sense numbers, common sense terms, like how much will this cost? How often will we be making this decision? Things that really speak to the mobilization of the effort instead of just pure numbers and accuracy. So if you have the data early enough, you have an action to take, and we are accurate enough to have a impact, then it's time to move on, okay? And so, small example, we might say, let's try and forecast demand for our system by looking at, historical EHR admission schedules and some discharge predictions and vitals maybe of the patients that are in there. Do we really have an action to take? This is pretty high level. It may not be the case, but you may have a group that's interested in adjusting their staffing or assignments based on this kind of information, in which case we have an action to take. Then we have to figure out, is it accurate enough to make a difference? So this is the kind of thought we have to put use cases through. This is just super high level, just to point out the idea again. You need early data that is actionable, accurate enough to make an impact. Okay, So what do we actually do when we're going to be predicting? We just do these couple of things. It's actually pretty straightforward. First of all, we gather data. Now, in the machine learning and predictive space, you may hear this referred to as gathering features or engineering features, but it is nothing more than gathering data, getting data together. You can think of it as simply as what will the table look like? If I had to put this into an Excel tab, what is it going to look like? What are the columns? So you can imagine, depending on the task, you'll need to gather different things. It may be clinical vitals or lab values, or it may be operational, like what was the occupancy at that point in time? What was our staffing level? Something like that. It could be demographic about the patient, age, comorbidities, social determinants of health, something like that. From there, besides just getting to raw information, there is usually some sort of feature engineering. So this is beyond the raw data that's available. What other summarizations or aggregations of the data might I create that could produce more information about the target I'm trying to predict? So here it's things like summarizing change over a period of time. So instead of every measurement value from the past 24 hours, it's what is the overall trend, up, down, or flat over the last 24 hours? Or what is the slope of the trend? You can imagine some simple math here can turn 24 observations into one that's more meaningful. Rate of change is something that's often captured here. You might be looking for event counts in the past X or ratios of some sort, number of consults that have happened. So this is where we move from raw data that might be available in a very wide open format to something more structured and aggregated in order to inform on what we're trying to predict. So that's a data wrangling task where we are simply working with people that pull data or building queries ourselves with our SQL skills to pull information down and create it, and or using Python to do this sort of work with some of the unique capabilities that it allows us. After we gather information, there's another step we have to take. So we are working with computers, and computers like numbers. They are efficient with numbers. And so in order to take a variable that's, makes sense to a human, like a string value or a classification, and turn that into something that the computer can efficiently digest and use, we have to take our categorical variables. You can think of male versus female, or rating on some sort of scale. Anything that's non-numeric, think of like a string or a rating, needs to be turned into something numeric so that the computer can operate with it efficiently. And so we do that through something called encoding. And so there are multiple different types of encoding to fit what sort of categorical variable that you have. So one of the most basic ones you'll find if you're looking at this topic is called one-hot encoding. And so this is where every category that is in the column list becomes just a binary feature, yes, no. And so this would take an example like admission type. Let's say we have 3 different admission types that can come into the hospital. And instead of having one column that says admission type A, admission type B, and admission type C, it turns it into 3 columns. One for admission type A, that is just 0 or 1. It happened or it didn't. One for admission type B, 0 or 1. One for admission type C, 0 or 1. So you're probably already thinking about the issue that comes up here. If your categorical variable has a lot of possible values, one-hot encoding is going to create an enormous amount of columns. So that is a problem. That means that we have to have categorical variables that have a modest or reasonable count of unique values in order to be used efficiently in this sort of modeling. And so it's commonly the case that we have to engineer things to fit that so that we don't have thousands, hundreds of different categories within our data, we have to think of some sort of abstraction that helps make it more digestible so that the size doesn't grow to an unreasonable rate here. Another type of encoding would be rare label encoding. So this is where we have really infrequent categories. And we go ahead and put that into a new rare class when the frequency falls below some threshold. This helps to reduce the directionality, cardinality of these estimates. Because they are rare, they can hold next to no weight, and it's important when they're important to the information in the model that we treat those appropriately. And so, as you're building code and asking for the right type of encoding, you may want to add that into your prompt about building this script to say, in this exercise of prediction, I want to evaluate my categorical variables and find out if any of them should be handled with rare label encoding. That's the direction I go, right? This isn't about knowing every last detail about how rare label encoding works and how to code it out directly. It's about knowing it's necessary when we have labels that have very rare occurrence and handling it accordingly using generative AI and code to direct us and think through the problem of, do we want to use this approach or not? Next, there is ordinal encoding. And so ordinal encoding is when our categories have some relationship to each other that has a natural ranking to it. This would be when we have a hierarchy of value within the category. So you can think of something like low, medium, high, or a number of 5-star ratings. Something like that can easily be turned into numerical values, 1, 2, 3, or 1 through 5 in the two examples, so that 5 is represented as greater than 1. So this is nice when you have an ordinal relationship, because the one-hot encoding expands to all these extra columns, but ordinal encoding does not. You get to keep it in one column and just order it, top to bottom. And then your binary encoding is very similar to the one-hot encoding in that we're going to assign an integer to each one of the categories and encode it as 0 or 1, whether or not it has happened. But it uses log of n columns to capture information efficiently. It's just a whole lot less interpretable. All right, so moving on after that, we've got our data gathered. We've engineered some columns that are meaningful. We have figured out some encoding so our categorical variables can be digested by the algorithm. And next, we're going to move on to model selection. And so one primary consideration that you have to have up front before you start building out a pipeline to use different types of models is how important transparency is to you. Now, transparency really matters in healthcare because often we still need to gain the buy-in of our proponents and be able to describe how the modeling is making decisions. And so there are trade-offs when we use different types of models between how much we can interpret from how the model is thinking and its performance. It is not always the case, but in general, as we move to more complex models like neural networks or random forest or gradient boosting models, we are increasing performance oftentimes relatively, but we are losing the ability to interpret and use the model itself to talk about how did the model make its decision, meaning what features are most important from our data, in what weight is being given to each one of our variables in our data. You lose that kind of explainability as you move to the right-hand side of this. And in general, as the models get more complex, the transparency goes away. So this is something that you need to think about. And if you have a need for transparency or would like to prioritize it as you build your modeling pipeline, which we're going to talk about and see examples of later, in my code, you're going to want to think about this trade-off. If you have a deep need for transparency, you need to set out and build in that way. In fact, I would recommend having, a pipeline that is meant for when you need to do this in a way that has transparency prioritized versus wide open, or where you're really looking only for best performance, not thinking about transparency. But that's the general idea, general rule that you need to be thinking about. And it's kind of one way or the other, really. After that, we have to think a little bit about what type of prediction we're doing with two major categories so that we're pointing the code in the right direction. Are we trying to classify that something is part of a group or not? Or are we trying to pick out a value? Are we trying to say how much something will be? So those are two really simple things. It's are we trying to say yes, something happened or didn't? Yes, it's a part of group A, not group B, as in positive, negative. Will discharge to this location or some other in classification, or is it regression? Like how many days left in their length of stay, or what do we expect this lab value to be? Those are the two things we need to think about as we're walking our code through the different models and selecting a proper set of models to evaluate. And so that's the next thing is evaluating. Well, actually, we'll move into evaluating. We start that after we have the models that we want to use, we're going to have this pipeline of data, which I keep talking about. You're going to see in my code. We'll go out and look at that. The next thing that we do after we have models we want to use is we want to do some tuning of the parameters of those models. These are called hyperparameters. And the hyperparameters are just settings of the models. So you have choices to make. How many times should it split, in the instance of something like a tree? What should we set the learning rate or regularization rate in different algorithms? So each algorithm has a unique set of these hyperparameters that can be chosen. And you should not know what these are. This is not like, okay, now I'm going to give you a chart of what the hyperparameters are and what you should set them to. These help control how the model learns and how it generalizes outside of what you trained on, okay? So the right tuning of this helps improve accuracy without making the model memorize noise or things that it shouldn't be paying attention to. The reason we're doing this is to avoid overfitting. So we are going to evaluate a lot of different options for these parameters and try to pick the right middle point to avoid things like overfitting. Okay, we're also going to avoid underfitting, and I'll give you some visual intuition of what that means. But some common pitfalls that happen if we just go about this naively is we may pick too many parameters for our model, in which case the model learns a bunch of the noise in our training data. Another common pitfall would be to maximize just training accuracy irrespective of anything else. Because when we do that, we're going to maximize training accuracy on the data it sees during training, but not on new data. So that's what we're trying to avoid with setting these properly. So we want safeguards here, okay? And so there's a couple that come into play with this sort of training and hyperparameter tuning in some of these things. One of them is that we train the data, we validate the data and see how it does on a subset of the training data, and then we test it on brand new data. This is a common workflow that we do that we will bake into our pipeline so that the code will do this on its own. This is not us making a choice. We just always ask the modeling output to be tested in this way. We also use cross-validation, which is to split the data in a specific way so that it can be tested across many different folds of the data to ensure we have good stability of our results. Another safeguard here to help in avoiding the overfitting, at least, is to prefer simpler models. If there's an opportunity to do that without sacrificing performance, it's a good choice to make. We avoid overfitting so we don't make something like this, right? To me, this is the best possible way to to explain overfitting. If you were to just model how someone sleeps to build them a mattress, you might just look at one person and find the one way they sleep most of the time and build something crazy like this, as opposed to a mattress that more generally covers the sleeping patterns of the many people that will need to use it. So this is what we're talking about when we're talking about overfitting. In a modeling sense, here's what that looks like. You see this pattern of data that is the same across these three examples. It is this sort of parabola, downward facing in general, these green dots. And so on the far left, you're seeing an example of underfitting. That would be where we have a model and it is doing what we told it to, fit to the data as best as you can, but it's really not the right type of model, okay? And it's certainly not, really probably can't be tuned, to do what it's supposed to. The middle is what we would represent as optimally fit. It is not reacting to every movement in the data, but it's capturing the essence. And that's what we're aiming for, as opposed to the far right, which would be an example of overfitting. As you choose more complex models, as you hyper tune these parameters, you can get models to do these sorts of crazy choices that aren't actually meaningful. They're only reacting to the noise in our training data. So this is kind of definitional here of the underfitting and overfitting and some intuition of what we are trying to avoid. And so this underfitting really is when your modeling is too simple, and the overfitting is when your modeling is too complex relative to the training data available. There's some great information at this site here, infodiagrams.com, with some of this illustration to give you a little more intuition on it. So I keep talking about a pipeline. So I'm going to talk about it here, same idea as a workflow that we're going to go through when we do this to tune these parameters and get the right model and everything. And then most importantly, we're going to go out and look at code. So I'm just giving you the ideas so that you have some framework to think about the code that we will look at, which we'll use really more. So first of all, your practical guide for tuning. Start simple. Pick a baseline model, something simple, and just default parameters, okay? After that, we do something essentially like a search. We're going to do a systematic search across the parameters that can be set in these models to figure out where does it do best. And so we can do that in one of two ways. There's a grid search in which we are going to try all of the structured combinations of all of these parameters. And so you can make that as detailed or vague as you want, but you set up, hey, I want to test out the entire landscape and every possible combination of these parameters. Usually not advisable. Usually you want to do this in a broader format, or if you need efficiency, because maybe this is a big data set, you move on to this random search, which is a similar thing. We're searching across different types of what these parameters can be set at, but it is not every possible combination in a structured format. It is randomly searching through a wider array to figure out where are we getting better or worse, directionally through these different parameters. After that, we do something called regularization, which is applying penalties in order to keep the model generalizable. And so this will be baked into the pipeline that you'll see that I give you code on how to do. Another important thing is to stop early, that we don't just train and as long as the day is, but we want to stop as we start getting, reduced returns, where we're getting less errors and our performance is improving and stops improving by leaps and bounds. Then we start to slow down the training. And of course, we do a sort of final check where we lock in those hyperparameters and test it out against a holdout set of data to figure out how it would have done, presumably kind of in the wild, if we had just stopped training completely and start looking at new information as if we're using it to make the decision. Okay, so that's a lot of content. It's going to make more sense when we head out to code, but here's the key takeaways that I want you to have. Really important to think about, do we have the preconditions met? That we'll have the data early, there's an action to take, and we've got accuracy that's meaningful. Next, we just got to prepare data. Pull information or gather information from others that could be useful for making this prediction, relevant clinical things, operational information, those sorts of items. And then we might engineer some of those features to pick up rates of change or averages over time or something like that to turn it into even more meaningful information on the prediction we're trying to make. Then we make a choice about what kind of models we're interested in. If we really need to work towards interpretability, we just sort of limit to a core set of models that are useful for that. If we're really more interested in performance and interpretability is not important, we have a wider set of possible modeling that fits, and we use those in our pipeline as opposed to the simpler ones. That's kind of it. We're kind of making a fork in the road there. After we've got our set of models we're going to try, we'll search to tune these hyperparameters within each to figure out which one, where we need to set these in order to get good performance that will generalize out to real data. Oh, and that's it. That's the key takeaways that I wanted you to understand about what we're doing in predicting in hospital analytics with Python. So excited to take you out and show you that in code and hand over to you basically a fully working script that's ready that, hey, guess what? I built through AI that is just phenomenally detailed and rigorous, far beyond what I could personally code out and produce, even myself. So this keeps changing how we operate and accomplish these things, but I'm excited to show it to you and where it's at because it allows us to go further faster, test ideas faster, and get to meaningful output so much quicker. So stay tuned. Let's go look through some code.